Like ammonia, amines are also basic in nature. Their basic nature is due to the presence of a lone pair of electrons on the nitrogen atom. This lone pair of electrons is donated to the proton of an acid to form a new bond. Amines are weak bases as they combine with water to produce fewer hydroxyl ions per unit volume. For example, an alkanamine combines with water to produce hydroxyl ions, as shown in the equation here. By applying the law of mass action to the equation, the base dissociation constant or basicity constant Kb equal to the product of molar concentrations of RNH3+ and OH- divided by RNH2. You get an idea of the relative basic strength of amines from their Kb or pKb values. The larger the value of Kb or smaller the value of pKb, the stronger is the base. By observing the pKb values listed in the table, we can say that aliphatic amines are stronger bases than ammonia. On the other hand, aromatic amines are weaker bases than ammonia. The Kb or pKb values of amines are affected by factors like the inductive effect of the groups present in amines, the ease of solvation of protonated amines, and steric hindrance. Consider the inductive effect of an alkyl group of an alkyl amine. Since it tends to donate electrons, an alkyl group R pushes electrons towards the nitrogen atom and thus makes the lone pair of electrons more available to the proton of the acid. Moreover, the alkyl ammonium ion formed from the amine is stabilized due to the dispersal of positive charge by the plus inductive effect of alkyl groups. Hence, alkyl amines are stronger bases than ammonia. Thus, the basic nature of aliphatic amines increases with an increase in the number of alkyl groups. Therefore, the basicity order of aliphatic amines in its gaseous phase is tertiary amine is greater than secondary amine is greater than primary amine is greater than ammonia. On the other hand, the basicity order of aliphatic amines in its aqueous phase is ammonia is greater than primary amine, is greater than secondary amine, is greater than tertiary amine. This can be illustrated on the basis of the ease of solvation of cation. The positive charge on the nitrogen atom is also stabilized by the effect of solvation in aqueous phase. The smaller the size of the ion, the greater will be the solvation with water molecules and more stabilized will be the ion. Thus, the order of basicity of amines in its aqueous phase is exactly opposite to the order based on inductive effect. Another important factor that affects the order of basicity is steric hindrance. If the size of the alkyl group is small, like the methyl group, then there is no steric hindrance to hydrogen bonding in its aqueous phase. If the size of the alkyl group is larger than the methyl group, then there is steric hindrance to hydrogen bonding in its aqueous phase. As the size of the alkyl group increases, the steric hindrance to hydrogen bonding increases, and the basicity decreases. Thus, the relatively basic strength of primary, secondary, and tertiary aliphatic amines is due to the combination of inductive effect, solvation, and steric hindrance. Now let us consider the order of basic strengths of aromatic amines. By observation, the pKb values of aromatic amines are quite high. This can be explained on the basis of the resonance stability of aryl amines and aryl ammonium ions by taking the example of aniline or aryl amine. The NH2 group in aniline or aryl amine is directly attached to an aromatic nucleus. As a result, a lone pair of electrons on the nitrogen atom is in conjugation with the aromatic ring, thus making it less available for protonation. On the other hand, the protonated aniline or anilinium ion obtained by accepting a proton can have fewer resonance structures than aniline. You know that greater the number of resonance structures, greater is the stability. Thus, aniline is more stable than the anilinium ion. Hence, the proton acceptability or basic nature of aniline or other aromatic amines would be less than ammonia. In case of substituted aryl amines, electron-donating groups such as methyl, ethyl, and methoxy increase the basic strength, whereas electron-withdrawing groups like NO2, X, SO3H, COOH decrease the basic strength. Here's a problem for you to try. Arrange the given amines in descending order of their basic strengths. Try to work out the answer yourself before checking the solution. The descending order of basic strengths of the amines and ammonia is dimethyl amine is greater than ethyl amine is greater than ammonia. This is explained on the basis of plus L effect of the alkyl groups. More is the number of alkyl groups, more will be the plus I effect. Here's another problem. Arrange the given amines in ascending order of their basic strengths. Try to work out the answer yourself before checking the solution. The ascending order of the basic strengths of these amines and ammonia is: paratoluidine is greater than aniline is greater than p-nitroaniline. Here, NO2 has a minus I effect and is thus less basic than aniline, while methyl group has a plus I effect and is therefore more basic than aniline. The laboratory method for the preparation of amines involves the reduction of nitro compounds. The reduction of nitro compounds can be carried out either by catalytic reduction using hydrogen gas in the presence of finely divided nickel palladium or platinum, or by using active metals such as iron, tin, and zinc in the presence of concentrated hydrochloric acid. In this reaction, the nascent hydrogen produced by the action of active metals with hydrochloric acid reduces the nitro compounds to amines. Note that both aliphatic and aromatic primary amines can be prepared by the reduction of the corresponding nitro compounds. For example, nitroethane on catalytic reduction or reduction in the presence of tin and HCl or iron and HCl gives ethanamine. Similarly, nitrobenzene on catalytic reduction or reduction in the presence of tin and HCl or iron and HCl gives aniline. Reduction with iron scrap and hydrochloric acid is preferred over tin and HCl. This is because the ferrous chloride formed in the reaction between iron and HCl undergoes hydrolysis and releases hydrochloric acid. Thus, only a small amount of hydrochloric acid is required to initiate the reaction. Amines can also be prepared by the ammonolysis of alkyl or benzyl halides. In this method, the carbon-halogen bond in alkyl or benzyl halides is cleaved by the nucleophile ammonia. This process of cleavage of a carbon-halogen bond by ammonia is called ammonolysis. It is also referred to as Hoffman's ammonolysis reaction in the honor of the scientist who worked on it. In this reaction, amines are produced when a mixture of an alcoholic solution of ammonia and alkyl or benzyl halide is heated in a sealed tube at 373 Kelvin. For example, when a mixture of chloroethane and alcoholic solution of ammonia are heated in a sealed tube at 373 Kelvin, a mixture of ethanamine, N-ethyl ethanamine, N-diethyl ethanamine, and tetraethyl ammonium chloride salt is produced. This is a nucleophilic substitution reaction where the halogen atom is substituted by the amino group. The primary amine thus obtained acts as a nucleophile and reacts further with more of alkyl halide to form secondary and tertiary amines as well as quaternary ammonium salt. The free amine can be obtained from the ammonium salt on treatment with a strong base such as sodium hydroxide. Ammonolysis has the disadvantage of yielding a mixture of primary, secondary, and tertiary amines besides a quaternary ammonium salt, which is difficult to separate. However, the actual composition of the reaction mixture depends upon the ratio of alkyl halide and ammonia used. If an excess of alcoholic solution of ammonia is used, then a primary amine is formed as the major product. However, if excess alkyl halide is used, then a quaternary ammonium salt is formed as the major product. Amines can also be prepared by the reduction of nitriles and isonitriles. The reduction of nitriles with lithium aluminium hydride or with hydrogen in the presence of catalysts such as platinum, nickel or palladium yields primary amines. For example, ethane nitrile on reduction with lithium aluminium hydride or catalytic reduction gives ethanamine. This reaction has synthetic importance as it is used to step up the carbon chain. Alkyl nitriles can be easily prepared by the action of alcoholic sodium cyanide or potassium cyanide on alkyl halide. Alkyl nitriles thus formed are reduced to get the primary amines. This is an excellent method for the preparation of primary amines. For example, methyl bromide on treatment with alcoholic sodium or potassium cyanide gives ethane nitrile. This on reduction with hydrogen in the presence of nickel as the catalyst gives ethanamine. The reduction of isonitriles or carbyl amines yields secondary amines. For example, ethyl isocyanide on reduction gives ethyl methyl amine, which is a secondary amine. In this method, we get only secondary amines in which one group is always the methyl group. Another method for the preparation of amines is the reduction of amides. Amides on reduction with lithium aluminium hydride yield amines. For example, ethanamide on reduction with lithium aluminium hydride gives ethanamine. A convenient method for the preparation of aliphatic primary amines is Gabriel's phthalimide synthesis. In this method, phthalimide is treated with ethanolic potassium hydroxide to yield potassium phthalimide. This potassium salt of phthalimide, on heating with a suitable alkyl halide, gives N-substituted phthalimide. The subsequent alkaline hydrolysis of N-substituted phthalimide results in the formation of the corresponding primary amine. For example, phthalimide on treatment with alcoholic potassium hydroxide gives potassium phthalimide. This, on heating with ethyl iodide, gives N-ethyl phthalimide. The alkaline hydrolysis of N-ethyl phthalimide gives ethyl amine and phthalic acid. Let us look at yet another important method for the preparation of amines. Hoffman's bromamide degradation reaction. Hoffman developed a method for preparing primary amines by treating an amide with bromine in an aqueous or alcoholic solution of sodium hydroxide. For example, ethanamide on treatment with bromine in the presence of sodium hydroxide gives methanamine. Note that in this reaction, the resultant amine formed has one carbon atom less than the parent amide. Hence, this reaction is used to step down the carbon chain. Let us look at the mechanism of the reaction. As you can see, the first step involves the halogenation of amide to yield N-haloamide. The second step is the abstraction of hydrogen ion by the hydroxide ion. This results in the development of a negative charge on the nitrogen atom. Step 3 involves the separation of halide ion, resulting in the formation of an intermediate with an electron-deficient nitrogen atom. Step 4 involves the migration of the alkyl group from the carbonyl carbon of the amide to the electron-deficient nitrogen atom. This results in the formation of alkyl isocyanate. The last step is the hydrolysis of alkyne isocyanate to yield a primary amine with one carbon atom less than the parent amide. With the knowledge that we have acquired about the methods for the preparation of amines, let us now carry out some conversions. Benzene to aniline, chloroethane to propanamine. In the conversion of benzene to aniline, the first step involves the nitration of benzene using the nitration mixture to nitrobenzene. The nitrobenzene formed in the first step is reduced to aniline in the presence of iron and concentrated hydrochloric acid or by catalytic reduction. Let's proceed to the conversion of chloroethane to propanamine. Note that this conversion involves the stepping up of the carbon chain. To achieve this, chloroethane is first treated with an ethanolic solution of sodium cyanide to yield propane nitrile. In the next step, propane nitrile is reduced by active metals like tin, iron, or zinc in the presence of concentrated hydrochloric acid or by catalytic hydrogenation to give propanamine. Dizonium salts have the general formula Rn2X, where R is an aryl group. The counter ion X- may be a chloride, bromide, or hydrogen sulfate, or a tetrafluoroborate ion. The dizonium group consists of two nitrogen atoms, triply bonded to each other with an overall +1 charge. Aryl dizonium salts are used as intermediates to synthesize a wide variety of organic compounds. To name dizonium salts, add the word dizonium to the name of the parent hydrocarbon. This is followed by the anion name. Consider the compound shown here. There is a dizonium group plus an ethyl group at position 4 on the benzene ring with the chloride anion. The correct name of this compound is para-ethyl benzene dizonium chloride. Can you name this aryl dizonium salt? Notice that there is a fluorine substituent at position 3 of the ring, or the meta position with the hydrogen sulfate anion. This compound is named metafluorobenzene dizonium hydrogen sulfate. Primary alkyl dizonium ions are not very stable. They decompose easily and tend to be explosive when dry. Dizonium salts are stable only for short times at low temperatures. Resonance structures help to stabilize the ion by delocalizing the positive charge around the aromatic ring. To prepare aryl dizonium salts, aniline is reacted with nitrous acid at 273 to 278 Kelvin. The nitrous acid is generated in situ by the reaction of sodium nitrite with hydrochloric acid. The overall scheme is summarized here. Due to the low stability of the dizonium salt, it must be used immediately after preparation. To prepare benzene dizonium chloride in the lab, a solution of aniline is prepared in hydrochloric acid and placed in a beaker of ice. The sodium nitrite solution is also cooled on the ice. The solution of sodium nitrite is then added very slowly to the solution of aniline in hydrochloric acid, keeping the temperature below 5 degrees Celsius at all times. If you use a different acid, you will get a different anion for the salt. Benzene dizonium chloride is a colorless, crystalline solid. It dissolves readily in water It is stable in cold water but reacts with warm water. Benzene dizonium fluoroborate is insoluble in water. It is stable at room temperature. The reactions of aryl dizonium salts can be sorted into two classes. Many reactions of benzene dizonium salts involve the displacement of the dizonium group, as nitrogen is an excellent leaving group. Aryl dizonium ions can also undergo coupling reactions, using the nitrogen atoms of the dizonium group to link to another aromatic ring. We first consider the reactions that involve the displacement of the dizonium group. The first group of reactions that we will discuss are known as the Sandman reactions. In these reactions, the dizonium group is replaced by a chloride, bromide, or cyanide ion in the presence of copper-1 ions. Nitrogen molecules are released as a byproduct of the Sandman reactions. Here is a problem for you to solve. Predict the major organic product of this reaction. The first step of the process converts 2-aminotoluene into the corresponding aryl dizonium salt. You should recognize the second step of the process as a Sandman reaction. Under these conditions, the dizonium group will be replaced by a nitrile group. In the Sandman reactions, the dizonium group is replaced by a chlorine or bromine group. To carry out these transformations, the dizonium salt solution is treated with the appropriate halo acid in the presence of copper powder. In general, yields for the Sandman reactions are lower than for the analogous Sandman reactions. Try to solve this problem on your own before checking the answer. Write equations showing the synthesis of this compound from an appropriate aniline derivative using the Gattermann reaction. With these types of problems, working backwards can be a very effective strategy. We need a bromine atom at position 4 on the aromatic ring. So we can carry out a Gattermann reaction using a Dizonium group in the correct location. We can make the Dizonium salt from the appropriate aniline derivative. Let's put it all together, working forwards from the aniline derivative that we need. We can convert the aniline derivative into a Dizonium salt by treating it with nitrous acid. Subsequently, we can treat the Dizonium salt solution with hydrobromic acid in the presence of copper powder to form the desired product. The Dizonium group can be replaced by iodine ions if the Dizonium salt solution is treated with potassium iodide. This reaction forms iodobenzene as the primary organic product. Try to answer this question on your own before proceeding. Draw the major organic product of this reaction. You should recognize the steps involved. Step 1 produces an aryl Dizonium ion. In step 2, treatment with potassium iodide replaces the Dizonium ion with iodine. The Sandman reaction is a method for making aryl fluorides. In the first step, a primary aryl Dizonium salt is treated with fluoroboric acid to make an aryl Dizonium fluoroborate, which precipitates. Next, the dry Dizonium fluoroborate is heated until it decomposes, releasing an aryl fluoride. Can you give the structure of the expected product for this reaction? You should recognize this as the Sandman reaction. The amine group will be transformed into Dizonium group and ultimately be replaced by fluorine. Reductive deamination of primary aryl amines replaces the amino substituent by hydrogen using a Dizonium salt as an intermediate. When the Dizonium salt is treated with a mild reducing agent such as hypophosphorus acid, sometimes known as phosphenic acid, the Dizonium ion is reduced to an arene. Alternatively, this can be carried out using ethanol. Can you complete this reaction? In the first step, the corresponding Dizonium salt is prepared. Next, the Dizonium group is replaced with a hydrogen atom. Nitration reactions replace the Dizonium group by a nitro group. First, prepare Dizonium fluoroborate by reacting the aryl Dizonium chloride with fluoroboric acid. When the Dizonium fluoroborate is heated with aqueous sodium nitrite in the presence of copper, the Dizonium group is replaced by a nitro group. Phenols are readily produced from Dizonium salts. These reactions cause the Dizonium group to be replaced by a hydroxyl group. To carry out these reactions, acidify an aqueous solution of the Dizonium salt by adding sulfuric acid at 100 degrees Celsius and heating it. Azocoupling reactions are electrophilic substitution reactions that take place when a Dizonium salt is reacted with a phenol or aniline derivative. In these reactions, the Dizonium cation acts as an electrophile, while the electron-rich compounds such as phenols and amines act as nucleophiles. The aromatic rings are joined via the nitrogen atoms. The azo products of the coupling reactions have extended conjugation involving both the aromatic rings. As a result, the products are highly colored. They are often used as dyes. For example, para-hydroxyazobenzene is an orange dye. Para-aminoazobenzene is a yellow dye. As we have seen, Dizonium salts are very good intermediates for introducing a variety of functional groups onto an aromatic ring. They allow for substitution patterns that cannot be prepared by direct substitution of benzene or substituted benzenes.